API VIII Calculation Masterclass. This Masterclass section focuses on the calculation section of the 2026 API VIII body of knowledge. The video is broken down into 3 parts. Part 1, Corrosion Rate and Remaining Life. Part 2, Internal Pressure and MAWP. Part 3, Static Head and Advanced Examples. Part 1, Corrosion Rate and Remaining Life, Sections 7.4 and 7. 1. We begin with corrosion rate because every calculation in this section depends on understanding how thickness reduces over time. Over the service life of a vessel, it continuously loses material, in this case metallic materials, due to corrosion, erosion, or other damage mechanisms. The goal of conducting thickness measurement during inspection is to measure how much of the original material has been lost. Metal loss, defined in API VIII Section 7.4, is the difference between the original thickness and the current measured thickness. For example, if the original thickness is 24 mm and the current thickness is 20 mm, metal loss equals 24 minus 20 is equal to 4 mm. This tells us how much damage has already occurred, but it does not tell us how serious it is. To understand the seriousness, we must determine how fast the damage is happening, and this, ladies and gentlemen, is referred to as the corrosion rate. Corrosion rate, defined in Section 7.1, is the rate of metal loss per unit time. The formula is metal loss divided by time. Using the same example, if 4 mm is lost over 4 years, corrosion rate equals 4 divided by 4 is equal to 1 mm per year. This value is extremely important because it allows us to predict future condition, not just past damage. Once corrosion rate is known, we can estimate how long the vessel can safely operate before reaching a thickness at which it can no longer sustain the pressure it was meant to withstand. API VIII Sections 7.1 and 7.2, Remaining Life. Now that we understand corrosion rate, the next step is to determine how long the vessel can safely remain in service. This is called the remaining life. Remaining life answers a critical question. How long before the vessel reaches its minimum allowable thickness? To determine this, we first need to know how much thickness is left before failure. This is called remaining corrosion allowance. The remaining corrosion allowance is defined in API VIII Section 7.1 as actual thickness minus required thickness. The required thickness, often called the pressure design thickness, is the minimum material thickness that was approved by design to safely withstand pressure loads for the equipment. For example, if the current thickness is 20 mm and the required thickness is 14 mm, remaining corrosion allowance equals 20 minus 14 is equal to 6 mm. The 6 mm represents the usable material left before the vessel becomes unsafe or unable to sustain applied pressure. However, this still does not tell us how long the vessel can operate before it gets to a thickness where it is no longer unable to sustain applied pressure. To know that, we must combine our Ca with corrosion rate to generate what we call the remaining life. Remaining life, which is the needed time to retirement, is defined in section 7.2 as remaining corrosion allowance divided by corrosion rate. Understanding the remaining life helps to predicted time to failure or time to retirement. It changes with corrosion rate, which is why continuous monitoring of metal degradation is essential. Using the previous corrosion rate of 1 mm per year, remaining corrosion allowance of 6 mm. Remaining life equals 6 divided by 1 is equal to 6 years. This means if conditions remain the same, the vessel will reach minimum thickness in 6 years. It is important to understand that this is a prediction based on current data. If corrosion rate increases or conditions change, the remaining life will reduce. This is why inspectors must continuously monitor corrosion and update calculations during each inspection cycle. API 510 Section 6. Inspection Intervals. Now that we know how to calculate remaining life, the next step is to determine when the vessel should be inspected. And this is the inspection interval. This is defined in API 510 Section 6. Unless justified by an RBI assessment, the period between internal or on-stream inspections shall not exceed 1/2 the remaining life of the vessel or 10 years, whichever is less. The general rule is that the interval shall not exceed 1/2 of the remaining life or 10 years, whichever is less. Using our example where remaining life is 6 years. Half of the remaining life is calculated as 6 divided by 2 is equal to 3 years. Therefore, the inspection interval is 3 years. This means the vessel will be inspected at 3 years, well before it reaches the minimum thickness at 6 years. If corrosion rate is not known, remaining life cannot be calculated. In this case, the interval shall not exceed 5 years. There is also a special condition for short remaining life. If remaining life is less than 4 years, the interval may be the full remaining life, but it shall not exceed 2 years. This approach prevents extremely short inspection intervals while still maintaining safety. Deferred inspection. A deferred inspection allows a short delay of an inspection and is limited to 10% of the interval or 6 months, whichever is less. It is important to understand that deferral does not create a new inspection interval. It only shifts the due date slightly. RBI may be used to extend inspection intervals, But this is based on risk and does not change how these calculations are performed. We now move on to joint efficiency. Section 8 Division 1 of the ASME Code subsection. UW3, UW11, UW12. Joint efficiency. A welded joint is not as strong as solid material. Joint efficiency represents how strong the weld is compared to the base metal. Section UW12 Joint efficiencies. Table UW12 provides joint efficiency, E, values for welded joints. Joint efficiency is judged and determined by the joint type and extent of NDE examination. It does not depend on the type of NDE examination of other joints. Why do we need joint efficiency? The correct value of E is essential for pressure vessel design calculations and code compliance. Joint efficiency is determined using ASME Section 8, specifically UW3, UW11, and UW12. Weld category UW3. ASME Section 8 Division 1, UW3, classifies welds according to their location and function within a pressure vessel. Category A. They include longitudinal seams and other highly stressed pressure boundary welds found in shells, heads, spheres, and hemispherical head connections. They are longitudinal seams, critical pressure boundary welds. For a pressure vessel, Category A weld, which is the longitudinal weld, is very important. It sustains the highest stress under internal pressure. Category B. This consists of circumferential welds, such as those joining shells, transitions, and most formed heads to shells. They are circumferential welds, shell-to-shell and head-to-shell joints. Category C. Category C welds include attachment welds connecting flanges, tube sheets, and flat heads to shells, heads, nozzles, or transitions. They are flange attachments, tube sheet attachments, flat head attachments. Category D applies to nozzle and communicating chamber attachment welds connected to shells, heads, spheres, or transitions. They include nozzle connections, communicating chamber connections. Category F welds are tube-to-tube sheet welds as specified by UW20. Radiography type, UW11. Section UW11 defines the type of radiographic examination performed on the weld. The common types are full radiography, spot radiography, and no radiography. The level of inspection determines confidence in the weld quality. Joint efficiency values, UW12. Section UW12 provides the joint efficiency values based on weld type and radiography. For most exam problems, the key values are Full radiography gives efficiency of 1.0. Spot radiography gives efficiency of 0.85. No radiography gives efficiency of 0.70. How to use the table. How to use ASME Table UW12. Purpose: determine the joint efficiency E used in pressure vessel design calculations. 1. Identify the joint type. Match the weld to the appropriate type number 1 to 9 in Table UW12. 2. Determine the joint category. Category A, longitudinal joints. Category B, circumferential shell joints. Category C, head-to-shell joints. Category D, nozzle-to-shell/head joints. 3. Check limitations. Verify any applicable thickness, diameter, offset, or construction restrictions. 4. Determine the extent of examination. Full RT or UT. Spot RT or UT. No RT or UT. 5. Read the joint efficiency E. Select the value from the corresponding examination column. Examples. Type 1, full RT or UT, E equals 1.00. Type 1, spot RT or UT, E equals 0.85. Type 1, no RT or UT, E equals 0.70. Type 2, full RT or UT, E equals 0.90. Importance. More extensive examination generally results in a higher E, allowing greater joint strength credit in design calculations. Memory aid. Check joint type, then joint category. Verify limitations. Check examination level. Finally, select joint efficiency E. Practical understanding of how joint efficiency works. Joint efficiency directly affects vessel strength. A lower efficiency means the weld is weaker. To maintain safety in the case of a too low joint efficiency, the design must compensate, usually by increasing thickness or reducing allowable pressure. Simple application question. If a vessel has a Category A weld with spot radiography, what is the joint efficiency? From the table, the efficiency is 0.85. Critical exam insight. The important thing to remember is this. Joint efficiency affects calculations directly. A decreased joint efficiency produces a reduced allowable pressure, even if thickness stays the same. Furthermore, when using Table UW12 for MAWP calculation, Section UW12, D, provides special rules for seamless vessel sections or heads. The code considers these seamless components to be equivalent to welded components of the same shape having Category A type number 1 welds. For circumferential stress calculations in seamless shells, or when determining the thickness of seamless heads, a joint efficiency of E equals may first be used when the spot radiography requirements of UW11, A, 5, B are satisfied. If the spot radiography requirements of section UW11, A, 5, B are not satisfied, or if the connecting Category A or Category B welds are type number 3, 4, 5, 6, or 8 joints listed in Table UW12, then a reduced joint efficiency of E equals 0.85 shall be used. Similarly, section UW12E applies to welded pipe and tubing. The code requires welded pipe and tubing to be treated in the same manner as seamless vessel sections and heads. This means the requirements of section UW12D are still used when determining the joint efficiency. However, there is one important difference. For welded pipes and tubing, the allowable tensile stress must be taken from the welded product stress tables, not the values listed for seamless products. End of Part 1.